So what we are going to study today is Lagrangian free particle. Lagrangian free particle. Lagrangian free particle. It will have from this understanding of Lagrangian of a free particle. We will have we'll just basically see from Lagrange how we have formulated Lagrangian formulation mechanics. How we can relate it to the Galilean classical mechanics which you have studied in your earlier classes. The Galilean first law of inertia in your earlier classes. So if we have any alternate formulation of mechanics, अगर आप एक ही बात को दूसरे तरीके से कह रहे हो, and but it has some advantages, but it should also contain your previous knowledge, what you have studied in your earlier classes, which includes law of inertia. So we are going to basically see how we can see Lagrange free particle, and from this we can extract the law of inertia in a logical sense. How? So before we are going to do that, before we are going to go for Lagrange free particle, so we have how we can just see Galilean relativistic relativity. How we can arrive this thing, what we have studied previously. अब इसमें ये है, for example, when we take a given particle, it's moving. So it may be moving uniformly, or it may be moving in a space which may be isotropic or anisotropic, or it may be moving in a sense where the notion of time in which the particle is moving, it may be homogeneous, or it may be inhomogeneous. So what homogeneous means? What do you mean by homogeneous? Homogeneous means the notion of time does not change from place to place. For example, if you have a clock measuring here, the measurement of clock, if it is 4 o'clock here, if you have clock here, it will also be 4 o'clock. Its measurement will not depend upon where you are measuring it. That is homogeneous. So it can also be inhomogeneous. Our measurement of time may depend upon the place which you are measuring. So if you take space anisotropic, or if you take space the measurement of time which may be inhomogeneous, our measurements will not lead to contradictions. Just as जो हमने कहा था, what was the advantage of going for Lagrangian dynamics? That we use generalized coordinates. There was freedom of how to choose given reference frame. For example, a given quantity k components translate होते हैं to x, y and z components. अगर हमारे पास एक homogeneous space, तो homogeneously components will also translate or transform. Got the point? But if we say that space is not isotropic, it is anisotropic, or our measurement of time you have is not homogeneous, it's inhomogeneous. So our assumptions regarding our assumptions will not hold, because the components will not transform either homogeneously or either isotropically. Got the point? So this is the point. So which will which will, I'll use the word, which will complicate our description. Which will complicate our डिस्कशन मीन्स दैट ये हमारे जो हमारा ये है फील्ड ऑफ स्टडी इसको थोड़ा सा मुश्किल बनाएगा, ठीक है, बिकॉज थिंग्स आर नॉट ट्रांसलेटिंग और ट्रांसफॉर्मिंग यूनिफॉर्मली फ्रॉम वन मेजरमेंट टू what important. So this much is fine. So now, if we don't take space and time this way, we don't take it anisotropic. Anisotropic means, isotropic means the value of space, whether it's x coordinate, y coordinate, z coordinate, it will be anisotropic means it's inhomogeneous. For example, the way you say, for example, if you say it's uniformly dense material, if you it's uniformly dense material, if you move this way, it will also have money here in the holes. If it's uniformly dense, so when you walk, you will have equal resistance whether you go to this direction, or that direction. If it is dense in one part more, less dense in another part, when you will move, you will have a resistance more in the direction in which it's more dense and less resistance in which it is less dense. So in the same way, so the components will not transform. So in the same way, in a homogeneous thing, the quantities or the components will uniformly. So this becomes a simpler system. So if we will not take space anisotropic, and if our measurement time is homogeneous, if we take a simple system, so how we are going to observe things for us? How? So now we are coming to our how we formulated Lagrangian dynamics. In Lagrangian dynamics, our thing was basically what? Coordinate, the time and velocities. The Lagrangian equation was like this: dl by dt, d by dt of dl by dx dot. So dx dot is velocity. We had a time parameter and velocity parameter. So if you take space and time, if you take space isotropic and time homogeneous. Homogeneous means the value of time does not depend from place to place. The value of time will uniformly wherever you are. So if you take these, because if you take anisotropy or inhomogeneity, it will complicate our description. It will complicate our. It's not कि ये description नहीं possible, वो भी हम ले सकते हैं, ठीक है? So if you take this simplest possible description, so what will how and we will take our yesterday's take a formulation mechanics which we call Lagrangian formulation mechanics. उसमें हमने due to velocity and time two parameters. अब ये अगर ये हम take it back way and we take homogeneous, so then जो हमारा Lagrangian है, it will not depend upon or because Lagrangian is depend upon x square. So Lagrangian depends upon x dot means it depends upon t velocity. It depends upon. So if it depends upon velocity, it doesn't depend in Lagrangian formulation. It doesn't depend upon distance x. It depends upon velocity. So if it doesn't depend upon x or radius vector, so it doesn't depend upon this. So it depends upon velocity. But we are presuming that space is isotropic. We are presuming space is isotropic. So if space is isotropic, the velocity component Vx, Vy, so it will equally transform the components of velocity in x direction, in y direction, they will also translate in an isotropic space equally. From this assumption, if you take space as an isotropic, you got the point. अगर हम space को isotropic ले लेते हैं, so it will uniformly translate. This means जो v का value है, the value of v is constant. The value of v is the value of v here, it is constant. So it means, तो अगर हमारे पास if we just take it this way, sorry, so since r is constant, so the first term will not contribute. Since dl by dx is an isotropic space, so it will be constant along dx dy, so it is also a constant. So if it's also a constant, we can say that the second term will be dl by dx dot, we write it as d is so if you integrate it to dl by d is constant, or from this you can say again integration, the Lagrange here is d is again integrated. So from this you can say in an isotropic and home space and homogeneous time, the Lagrangian in the given Lagrange, the velocity remains constant. What does it mean? What does it? So we have extracted the definition of inertial frames from this. Inertial frame, what is the inner definition of inertial frame? Which will have constantly moving frame, with uniform velocity or whatever, and observe all measurements are, okay. So the way you define. So from this, so we have, even if we formulate mechanics in the Lagrangian formalism, and we take these assumptions that space is isotropic, time is homogeneous, from this we can arrive at the definition of law of inertia, which you have studied in earlier classes. So this means Lagrangian formulation includes the inertial, our definition of inertial frame of reference. So this is a very interesting thing. V is also. So thus we conclude that in an inertial frame, any free motion takes. So if we are using words of book, in any inertial frame, any free motion takes the velocity which is both constant in magnitude and direction. Constant in magnitude and inertial frame. की definition क्या है? Constant in magnitude and in direction. So this is law of inertia. Law of inertia. Because we don't have Vx, Vy, Vz. So this means V is constant. We only take magnitude of V. So this means from this we have extracted from it from simple definition. So the exercise can be like this: from our definition of Lagrangian and keeping space isotropic, time homogeneous, how do we arrive at the law of definition of inertial frame of reference? So this is the exercise we have done. Okay. Now, इसमें अब एक और point है. Another point is that so it's not that there will be one inertial frame of reference. So if there is another inertial frame of reference which is moving vis-a-vis this inertial frame of reference, which is moving, which is also having a constant velocity, which is also having a, and you can relate this reference frame with the another reference frame. So this means that we can not have one inertial frame of reference, we can have as many possible inertial frame of reference can be found or can be extracted. So it's not If velocity is constant for this, so we can take any other velocity which is equally constant. So constantly moving inertial frames of references can be generated, and there is an infinite possible inertial frame of references can be generated if we take isotropy of space and homogeneity. So from this you can infer this theory of Axical. Okay, we can have this inference also. So the point to prove is that whichever formulation of mechanics is there, it should contain your, जैसे आप higher class में पढ़ते हैं ना, the algebra should contain arithmetic, है ना, lower. So it includes our understanding of Galilean inertial reference frame, and it should also say something more. No, it should have some advantage. That's why you are studying mechanics, classical mechanics, or Lagrangian mechanics. Okay. So this is one obvious advantage we have got. And if you study in your earlier classes, तो आपने अगर दो reference frames move कर रहे हैं, तो Galilean addition, velocity addition rule आपने पढ़ा होगा, है ना? How we can relate one reference frame, for example, you are moving with one velocity, there is another moving somebody moving, हम कहते हैं simply if it's moving in the same direction, you will add it relative velocity simply, which you have studied here. Or prime plus b relative velocity. This is a Galilean addition rule. अगर आपका एक का position vector है, the other is moving vis-a-vis in another reference frame. How we can relate these two reference frames, two velocities? The R may be plus or this will be plus or minus, depending upon if it is in the same direction or it is in the. So this is how we can relate one measurements in one reference. You might have done many problems in class, upstream, downstream. So basically, what we are studying, there is one inertial frame, measurement in one inertial frame, and how we can see measurements from another frame, such that they should not lead to contradiction. They should not lead to. There is one innate notion there. The notion of time, जो है, that is. So which we will see, if you might have studied special theory of relativity. There, the time notion of time is not homogeneous. So you have Galilean inertial this law. It's been modified by Lorentz modification. Or when you study Lorentz special theory of relativity, or when you study electrodynamics, relativistic formulation of electrodynamics. So this law doesn't. Why it doesn't hold? Because we assume that the translation of time, the measurement of time is not homogeneous. What do you mean by that? It means that the if you have a clock here and you are measuring something, the value of time does not depend from where you are measuring. It is time is uniformly flowing in the same way wherever you are in the universe. So from these two simple assumptions of isotropy of space and homogeneity of time, and using our yesterday's Lagrangian way of looking at things, we can arrive at not only our previous definition of Galilean inertial frames, but also equivalence of, you can generate infinitely many inertial reference frames, and the measurements of these reference frames can follow this rule or law addition rule, which is also called. Okay? Now we are going to come up all in we are going to just see. So here जो हमारा ये है isotropy of space and homogeneity of time. So they are, think over it. ठीक है. So इसमें ये है कि जो for example when we take Lagrangian dynamics, for example the components of a given quantity, कोई भी component किसी why we take recourse to alternate coordinate systems. Just like आपने ग्रिफिथ में बहुत सारी problems की हैं, that some of the problems are taken to we go to cylindrical coordinate system, we go to spherical coordinate system. Why we go to that coordinate system? Because the components of that coordinate system को ऐसे choose it such that the components कैसे translate होते हैं space में. So the problem becomes easier. The problem becomes easier. So in the same way, generalized coordinates हमने जो use की हैं, which is depend upon velocity वहाँ पर नीचे. तो उसमें ये है कि how the coordinates transform the notion of flow, so it becomes important. So I'll just come to this point. अब हमारे पास है, we are going to take Lagrangian free particles. Lagrangian of free particle in a sense, जिस तरह हम कहते हैं ना कि everybody moves in its state of rest or uniform motion unless acted on by external force. That force will make it to change its velocity to the. So you can have उसका equivalence ये free particle. मतलब free particle means what? वही free particle is not acted upon externally by anything. So you can see it that way. अब हम what we are going to do is we are going to take just like in this thing that R is equal to R prime plus addition with only T is equal to T prime. So how we can relate two reference frames? How we can relate two reference frames key measurement. So in the same way, how we can तो अगर हम Lagrangian of a given particle लेंगे, how we can relate the measurements of two reference frames. If one is moving at velocity v and another is moving at velocity v plus epsilon, v plus. So how we can relate them? That's our So if we take the velocity of one of the reference frame is v and another is v prime, so relating v and v prime as v plus epsilon. So I will just take this one. So Lagrangian of, so you can have Lagrangian की of ये है. Obviously, this is 1 by 2 mx. क्या है? Kinetic energy plus total energy of the system. अब Lagrangian है d by dv of dl by dx dot. तो इसका क्या है? 1 by 2 mx dot. mx dot. तो अगर हम Lagrangian were to take Lagrangian of a given particle, तो L of v square, ये mx dot है, so you can also write v prime को you can write it as v plus epsilon, but it's basically v plus epsilon into v plus. This is component to component. V square epsilon v and v epsilon. Yeah, yes. V epsilon. Okay, so this you can see. Now, what the book says, we just expanding this expression in powers of epsilon. In powers of epsilon. Epsilon is the sum. कोई हम if you start some particle, दूसरा particle start कर रहा है at some time के बाद या कुछ जो में कुछ होगा जो relative velocity हम करते हैं v and v plus epsilon. So epsilon is that infinitesimal amount by which some another frame or some other particle is moving. So expanding this expression in powers of epsilon and neglect in terms of Harold. Neglect in terms of Harold. अब आप करते हैं ना इसमें बाइनोमियल एक्सप्रेशन लगाते हैं प्लस एप्सिलॉन. अगर इस ये एप्सिलॉन को ऐसे करोगे बाहर b को बाहर निकालोगे v1 by epsilon by v स्क्वायर. ठीक है, इसको फिर आप फिर बाइनोमियल टर्म्स करोगे 1 plus 1 2. So if you do it that way, तो Lagrangian of v prime square is equal to Lagrangian of v square plus, and he is negative one of the terms he has. Second term को इसको ऐसे लिख रहा है. So I have it out doubt. Just try to work it out. So this is an exercise for you. जो इसकी second term है ना ये ऐसे लिख सकते हैं कि नहीं. ठीक है? So I do not have time. अब ये कह रहा है कि Lagrangian square है, Lagrangian is proportional to 1 by 2 and v square. And जो v है ना v के बदले हमने लिखा v और v प्राइम अगर इसको L prime is basically v prime square dot m v plus v square. Again, you can write it like this: v square plus v बड़ा वाला v plus 1 by 2 और m v. Now you can write this Lagrangian को हम फिर ऐसे लिख सकते हैं. So we are just doing nothing. We are taking two reference frames. एक की Lagrangian velocity v है, दूसरी की Lagrangian velocity है e plus epsilon. We are relating them. और जो L prime है, इसकी velocity है v plus e. So you can also write it as further. ये तो अपना Lagrangian of the original Lagrangian. The first started. ये Lagrangian है, मैं इसमें add small velocity. Lagrangian दूसरा वाला Lagrangian. ठीक है? You can again rewrite it as L prime is equal to L prime is equal to L plus d by dt of m और dot b. अब ये है b स्क्वायर आप करो b डॉट b, इसमें आप करो एक और d और by dt हो गया छोटा b, ये b है, ये b into b है प्लस and then neglect this term. तो हमारे you can write these terms also like this. जो Lagrangian of the system है, not only one particle, but a system of particles is that they have additive property. They have additive property क्या मिलेगा? अगर कोई सी ऑफ फंक्शन है ऐसे, if function is equal to f1 plus, so it's equal to c of f1 plus c of f2. So अगर कोई भी सिस्टम है, इसमें एक नहीं दो नहीं, अगर कोई कांस्टेंट होगी, कोई कांस्टेंट है, it will individually multiply to the subsystems of that group. इस तरह अगर कोई Lagrangian of a given system है, ठीक है, it's composed of one particle, two particles, three n particles. मगर जो relative velocity जो move करेंगे with regard to each other, अगर they constantly उनका होगा ना, जैसे phase difference होगा, they will constantly the addition or multiplication of constant with regard to these two reference frames, वो constantly multiply करेंगे, phase वही रहेगा, जैसे एक 5 किलोमीटर से चलेगा, दूसरा 10 किलोमीटर से चल रहा है, तो you will add, एक में आप ऐड करोगे 5 किलोमीटर, दूसरे में करोगे 5, ये 10 बन जाएगा तो 15 बन जाएगा, ठीक है। इसी प्रॉपर्टी को हम कहते हैं, so we write it like this: Lagrangian of a system is of this is what we say. One another point he is saying is that the Lagrangian of a system, if we denote it as like this, of a particle like this, dt, the value of mass will always come out to be, the value of mass is always positive. It's always positive. अगर ये नेगेटिव आएगा ना, the value of Lagrangian will come out to be, once you evaluate this integral, it will come out to be some minus value. अगर कुछ some minus value आएगा, then it will come closer to the, it will not be minimum by the principle of least action. Okay, this is one. And the other point which I wanted to emphasize again and again is since in Lagrangian we are using generalized velocities or generalized coordinate system. So कोई भी problem है, for example velocity है हमारे पास, this is velocity denoted by this. So the line element can be denoted in different coordinate systems differently. In rectangular coordinate system, line element is what? Dx square plus dy square plus. Basically, we are not interested in dx. We are interested in dx by dt or velocity. That is basically used here by dx dot. So first we should know dx. Line element क्या है? Line element in rectangular coordinate system is this. But in, for example, in cylindrical coordinate system, line element, the value of line element will be dr square plus r square d phi square dz square. And in this is cylindrical, this is rectangular, this is spherical. In spherical, the line element is dr square r square d theta square and r square sin square theta d phi square. Go to point. So in rectangular coordinate system, line element is this. In the cylindrical, you have to see which are the constants, which are the. So here five values. Here theta and phi values. If you remember. Now accordingly, this line element has to be converted into dl by dx, because we are interested in this velocity. So we can then formulate our problems of. So you have to define Lagrangian of a system. So before defining the Lagrangian of a system in generalized coordinate system, which coordinate system is suitable to solve that problem, which we are taking into consideration. And accordingly use this understanding. You have three coordinates, you can have four coordinate systems. And then when we actually solve practical problems, so how we can determine the Lagrangian of a given particle, two particles, n particles, system of particles. This is a general exercise. So in today's class we had some, एक तो हमने किया कि जो गैलीलियन रेफरेंस ये है, we extract it from Lagrangian of a given system. The second is that if we have relative velocity of one Lagrange of one particle with another particle, how we can relate it. Third is that the line element, how we can write it in a different coordinate system. And this line element, for example, I will just write it at this end. For example, the Lagrangian of this cylindrical coordinate system, the Lagrangian is written like this: r dot square plus r square pi dot square plus z. This is r dot square because the line element is equivalent to this. We have to find velocity. तो velocity निकालनी है। r dot किसके बराबर है? ये r dot square, ये r यहाँ कौन सा है? pi dot square, ये z dot square. So we can first state the problem. पहले हमको आना चाहिए how we can state problems. How can, if you know how to state the problem, how a problem is, then you can apply it to Lagrange of किसी भी system के लिए. Pulley problem, straight problem, bead है, and then there is something called constraints. You see it. Okay. How we can set a given problem. कोई अब motion है, motion is there. How we can have a Lagrangian of that system? How we can have? First, we should know how to set the Lagrangian of a given system of one particle, two particles. Then we can go for solving the Lagrangian. Solving the Lagrangian means what? And equation of motion. Equation of motion. Okay? We have to find the equation of motion.